Go ahead.
Cool. Hey everyone, I am Aniket Maurya, developer advocate at Lightning AI. In this live stream, we are going to talk about how you can deploy a diffusion model with Lightning app. So, before proceeding, we would like to hear your feedback. Here is a QR code and a link which you can scan to get a Google form, feedback form, and fill out the form to let us know how you like the event and what would you like to see in the next event, and we would definitely consider your feedback for our coming events. So today's agenda: introduction to diffusion models, text to image generator, building a prediction API, auto scaling the model server, and dynamic batching. And finally, we will also show you how you can deploy a custom version of stable diffusion. So, what is text to image generation? As you can see in this clip, you can enter a text prompt and you can generate an image based on the textual prompt. So the model works like in such a way that it learns a image distribution, and based on the given prompt, it can generate an image out of it. So this clip here is based out of Stable Diffusion, which is one of the most famous diffusion model these days. So if you are on social media, Twitter, Instagram, or anything, you must have seen amazing arts created by Stable Diffusion. Stable Diffusion is not only limited to generating images. As you can see, you can also generate some cool videos from Stable Diffusion models as well. And even some PhD biology people also have created some proteins from stable diffusion. If you want to learn more about diffusion models, here are two of the amazing resources. The first one is an YouTube video, Stable Diffusion Demystified by Daniela. And the second one is a newsletter from Sebastian that you can read to know more about different applications of diffusion models. So this live stream is mostly about how you can deploy a diffusion model, scale it to hundreds of concurrent users. So we will be focusing more on how you can do that. So let's move forward with deploying diffusion models. Muse. Recently, we deployed a product called Muse. It is a product basically which deploys stable diffusion in production, with 300 concurrent users. It has a lot of different functionality like auto scaling and dynamic patching. It also comes with an UI which you can play with. You can enter a text prompt and generate an image out of it. And if you want to learn more about this product, you can go to Lightning AI, yes, its blog. And also, you can just go to lightning.ai, Muse, and here you can enter a text prompt. Let's try the default text prompt and click on this Muse button. So it is going to generate an image out of the text prompt that has been entered here. Cool. And let's enter something else like cats and hats, something funny. So it is going to generate an, oh, so it also has a safety filter. This model has been generated on a lot of different kinds of image. So it might be possible that the generated image contains some unsafe content, and the safety filter will filter out the unsafe content for you. So you can see there is a cute cat wearing a hat here. So definitely play out with this UI, and to learn more, you can follow this blog right here. So this discusses a lot of things that we have done while building this product, and definitely read it out. So let's move forward. Muse is not just a stable diffusion app. It is a blueprint for deploying any kind of machine learning model. It can serve a model on a CPU or a GPU. You can select different kinds of GPUs. Like you can go to our documentation. You can select what kind of GPU you want. You can select a T4 GPU, an RTX, or anything that is available on the Lightning Cloud platform. The Muse app can auto scale its infrastructure based on the request traffic. It can also do dynamic GPU batching for requests. So if you have a GPU and you should be batching your requests to fully utilize the GPUs. Then it also has a React UI, which is connected to the Lightning Python backend, and it comes with a rate limiter pre-installed, so that if you deploy your app and if someone wants to do a DDoS attack, you are safe. It also has some system monitoring integration like Sentry. So how did we build this model server? So I'm going to take you through like some code snippet on how we built the first model server. So the model server basically first loads the model, defines some prediction functionality, and exposes a REST API for serving the stable diffusion model, where you can provide the text prompt and it will return you the image in a encoded format, which you can consume or you can render it on your UI. So building the model server. Here is a code snippet. I have a class called stable diffusion serve, which inherits lightning work here. And it also has a build model method. It can load a model from a given checkpoint. So it will load the stable diffusion model. Next, I have a prediction functionality defined. So it basically takes a prompt and generates an image and then returns the image encoded into base 64. We encode in base 64 because when we are returning the image, we need to encode the image in a string so that the client can consume it. Then the run method. The run method basically defines the whole flow, how our model server is going to work. So first of all, we initialize the model. Then we initialize the fast API app, and then we define a REST API. So our API path is /API/predict, and it basically takes the data, which is prompt, and returns the image. Finally, we launch the server. We launch our fast API server with an fast API app with a UVCon server. And once you run this app, you can go to the URL, and fast API comes with a Swagger document, which you can use to try out prompts and generate images. This was not a scalable solution. So I take a pause here for a few seconds and ask the audience, like, why do you think, what was missing that it was not scalable enough? So if anyone in the community, if you think there is an issue in the code model server, you can mention it in the comment. It serves, so Sanket has mentioned that it will serve one request at a time. Yes, that is correct. So that is an issue because it is going to serve one request at a time. So if there is a lot of users comes at the same time, it won't be able to serve to everyone, and there will be a lot of latency. Cool. So let me share the other things which makes it not scalable. So as Sanket said, the requests are being processed sequentially and there is no batching on the GPU. Also, we do not have a parallel server running. So we have just a single model server, which is going to take care of all the client requests. And now how did we overcome all these challenges? So we implemented a load balancer, which launch multiple parallel servers instead of single one, which can process the request from clients. And then the load balancer routes the client request to all these model servers, so that not only a single model server is busy in processing the request. And also we batch the incoming request so that we can utilize the GPU completely. Here is a experimentation that we have done. So we did run some experiments and measure the performance. So without batching, we were able to handle less than 5 concurrent users, which was very bad. And with batching, we were able to handle more than 10 concurrent users, and that was with only a single model server. Then we combined batching with more parallel number of model servers. So we were able to handle 100 concurrent users in a sustained way and 300 concurrent users in a burst way. So if 300 spontaneous users comes and try to use Muse, they won't get an error. Here is an architecture diagram of how Muse works. So in the bottom, you have a client with using Muse from UI. They hit on the Muse button and the request will go to the load balancer. So the prompt will go to the load balancer, which is responsible for dynamic batching and auto scaling. Then the load balancer also aggregate requests to do the dynamic batching. It will wait for a few seconds, and if it is able to aggregate, suppose if my maximum batch size is 10, so it will wait for a few seconds to gather 10 requests and batch it, and then it will send the batch prompts in one of the model servers. So these model servers are scalable. So if I have 3 model servers initially and the traffic increases a lot, these will increase. It can go to 4, 5, 6 based on what is the threshold you have defined maximum number of model servers. When the result is ready, it will return the generated image back to the load balancer, and then the load balancer will return it back to the client requesting the UI. So here is the Muse configuration that you can update according to your uh, use case. So here is initial number of workers, and initial number of workers is basically model server. So if you think that whenever you launch your application, you are going to receive a lot of traffic, so you can set this to a higher number. If you think you won't get a lot of requests, you can set this to 1. So only one model server will be ready to serve. And then auto scale interval. So the load balancer runs this job on every 30 seconds, which you can update here. And on every 30 seconds, it checks if the model server need to upscale or downscale based on the number of requests or traffic. Then we have maximum batch size. So it depends on the amount of GPU RAM that you have, you can process, or how you want to optimize for latency. So if you have a lot of, if you have high end GPU and with a lot of GPU RAM, you can set this to a higher number, maybe to 64 or 32. And if you have a GPU with less RAM, so you can set it to a smaller number, to 1 or for anything. Then you have batch timeout seconds. So the load balancer will wait for 10 seconds to aggregate 4 batches, 4 requests. If you set it to 1, the load balancer will wait for 1 second to aggregate 4 requests. It is not necessary the load balancer will aggregate 4 requests. Even if it gets 3 requests within 10 seconds, it will send the 3 batch requests to the model server. Then you can also specify the GPU type you want to deploy. So you can, again, you can go to our documentation and look up different kinds of GPUs available on the Lightning platform, T4, RTX, anything, and specify it here. Then maximum workers. So you can set this to anything, and suppose if you are like low on budget and you do not want to scale to hundreds of like maximum hundreds of model servers, so you can set this to a smaller number, maybe 5 or 10. And auto scale down limit. So this is the threshold which decides when to downscale. So if that number of requests is below auto scale down limit, the load balancer will automatically decrease the number of model servers. And auto scale up limit. If the number of requests is more than this particular threshold, your load balancer will automatically spawn more number of machines, more number of model servers to handle your traffic. All these things are taken care automatically for you. And in the last, you have something called load testing. And if you set this to true, uh, you will, when you launch the app, you will get a locust UI where you can enter some number of users, and you can do the load testing online, and you will get a very beautiful chart, and which will show you how is your app performing with RPS, concurrency, response time, everything. Cool. So now I'm going to give you a quick code walkthrough of the Muse code base. So I will go to github.com and the Muse code base. So if you want to access this code, you can. It is completely open source, and you can go to the Lightning AI organization. Here you will find Stable Diffusion deploy. So scroll down here in Muse components. I have Stable Diffusion serve here. So this is the code that I showed you in the slides. In slides, I had a simplified version of the code base. So you can see this is the Stable Diffusion serve class defined here. It downloads weights of the model, Stable Diffusion model, do some extraction and all. Then it loads the model and loads the safety checker. And finally, I have the prediction functionality here, which basically takes the prompt, generate the image, do the safety checker, and if there is some unacceptable content, it will replace the image with a warning image. And finally, I have a run method. In the run method, you can see I build the model. I have a fast API app, which is being created here. Then there are some events which has been created, and we have defined a REST API endpoint, which basically takes the prompt and returns the base64 encoded image here. And finally, we run the avcon server to host our fast API app. So this is the Stable Diffusion model serve, and let me show you the load balancer, which is responsible for handling all the model servers like upscaling, downscaling. So this is the load balancer. It is also lightning work. And if we come here in the run method, we start a fast API app, and what it does is again we have yes, predict method. And this predict method basically goes into each of the model servers. So it will pick each model server one by one and send the request. Also, this load balancer is handling the dynamic batching. So how it does is the load balancer has a batch or a queue. So it has you can think of it as a consumer and publisher. So whenever we receive a request, we publish it to a queue, and there is a consumer which takes the prompt from the queue, process it, and whenever the generated image is ready, we publish back to the result. And when the result is ready, we return to the client. Also, it has a update server method, which so the load balancer maintains a list of servers, which is basically when it is upscale or downscale, it gets updated. The older one gets deleted and the newer one gets added. So this is the logic written here. Let's see app.py, which integrates all this thing into a single flow. So in the root of this repo, you will find app.py. You can see from Muse, we have imported load balancer, different components like locust, stable diffusion serve, and slackbot. So this is the Muse flow. This is the root of our application. And here you can see everything is being initialized. The load balancer is here. The model servers are being initialized here. Slackbot component. Our React UI is initialized here. And if we go down in the run method, you can see this defines the flow. So we first run the load balancer, then we run the Slackbot. We will come to Slackbot later in the end of this talk. And we run the model serve. And when everything is ready, we do auto scaling. So if we go to auto scale, it basically checks in an interval, and you can see here upscale logic. So if number of requests is greater than upscale limit, we are going to add a new work here. So it is very simple. Create a work and just add the work. Then if we have to downscale, that is if number of requests is lesser than the threshold limit, we are just going to remove the work, which is remove one of stop one of the machines and remove it from the list. And finally we also have to update our servers after we add or delete one of the machines. So here we have called update server. And finally you can see we have the muse flow, which has some uh, HTML related stuff like title, description, and meta tags, which you can also provide. So this was the code base for Muse app. You can definitely check it out, and it is documented. You can try it out. You can try to run your own version, which I'm going to show you now how you can deploy your own version of Muse app. So first, let's go to Lightning AI app gallery. So if you go to lightning.ai and app gallery here, search Muse. By the way, this Lightning app gallery contains diverse set of machine learning applications, and which also contains research demos like CVPR, mask auto encoder, image search, clip, and if you go downward, it also have some cool MLOps related stuff like recommender system, AI powered hacker news, and in video search, reinforcement learning related apps. So a lot of different kinds of app are present here. You can come here. If the app is clonable, you can clone and modify the app according to your needs. So I have the Muse app here, and we already have tried it. But if you click on try it free, you will get to the uh, this page where you can try the app. And there is the another button called clone and run. So if you click on clone and run, it is going to copy this app, clone the fork this app, and run a version of this app in your Lightning account. So it is provisioning the machines, and then it will download the code, install dependencies, and once everything is ready, you will see this blue button here as active. So I already have one app already started for this. So if I click open app, you can see a version of this app is running in my cloud. And one of the cool feature is you also get to record your logs. So you have different components like load balancer, model serve, and Slackbot, and UI. So you can select one of the component and check the log for each of the components separately, which is very cool. You can also download your logs. And now let me show you how you can copy this code into your local system, then modify it according to your use case. So click on this view code from icon, and I can see download the app code. So I'm just going to copy it and then go to my terminal and just paste it here. So it has been downloaded into my local machine. So I will just launch this, and I have open app.py. I will scroll down. So here are the configuration that I showed you earlier in the presentation. Initial workers, auto scale interval, all these things are here. So I want to customize this app and customize few things like the kind of GPU I want to use, and number of initial workers, and batch size. So to run this app, you need to do lightning run app.py. So if you hit enter, this app will run you in your local laptop, in your local system. And when you want to deploy this app to your cloud, all you need to do is append double hyphen cloud, and it will be deployed on Lightning Cloud and in a very distributable and scalable fashion. So you can deploy it without knowing any cloud computing technology. Uh, so there is another cool stuff, that is you can set the environment variable directly from the terminal. So you can enter double hyphen env, and I want to set minimum number of worker as 2. Then I want to select the GPU type, which is um, so I know that if I type GPU, it will give me T4. So I want T4 GPU, which is relatively cheaper. And let's set the max batch size as, so this is, let me set it right here. So you can change in the code itself. Let's set it as 2. Also, you can name your app. So I will say Stable Diffusion live stream, and press enter. So this is going to upload my code into the Lightning platform, and once it is ready, it will take me to the lightning.ai, and where my app will be like provisioning everything for me. So the machine is being provisioned, and then it will download the code, install dependency. Once the app is ready, I can open it. It will be exactly like this one, which I showed you earlier. We can wait for a few minutes. It is a large app because we are instantiating and installing everything for the first time. So meanwhile, let me show you the Slack bot, which I've been talking again and again. So if you come to the Muse app page, in the bottom, you will see this Slack bot icon. And if you click here, you can install the Slack bot in one of your Slack workspace. So I am an admin of this Gradflow workspace. So I'm just going to install it here. So this app has been installed. Then let me go to Slack. Yeah, this has been added. Then I can generate images directly into Slack. So all you need to do is install the apps, then enter /muse followed by your text prompt. So generated image for text prompt, cats and hats, and here it is. So you can also install it to your Slack workspace and start generating image in directly in your workspace. Cool. So as you can see, it is installing dependency. It's gonna take some time, and we can move forward with the slides. Also, so when you have to deploy a Lightning app or any kind of application, you usually do it from, you can do it from the CLI. So you can do Lightning run app.py, or you can also hook this into a CI/CD of your choice. So for the Stable Diffusion app, for the Muse app, you can come to our GitHub repo, and here you will see we have a workflow defined for it. So whenever we want to do a release, we deploy it from the GitHub CI, from the GitHub action. So you can come here, check this. You can, we have this run defined here. So we just do Lightning run app, cloud, Stable Diffusion, and you can also do it in a similar way. You can hook it with Jenkins or something. Cool. So key takeaways. Lightning, with Lightning app, you can support a burst of 300 concurrent users, even more. So with the Muse app, we have showed it 300 concurrent users. If you can optimize it further, and you can deploy any kind of machine learning model, not necessarily stable diffusion or diffusion model. It is not it is understand it as a kind of a template which you can use. And also everything is in pure Python. There is no YAML or anything like that, so you have full control with the code. And then Lightning manages everything for you: cloud provisioning, GPU instance selection, disk allocation. So you do not have to worry about anything at all. You can just focus on your research, your code base, your and the engineering tasks, and not worry about how to manage cloud and infrastructure at all. Cool. So now I'd like to ask from the community, if you have any question, feel free to ask it in the comment section. I would be answering your questions.
So, Aniket, we have one question.
Yeah.
You can check it on StreamYard from Gustav.
Yes. Gustav has asked, can you show how to access a REST API endpoint for prediction of some model on Lightning Cloud using Python code on your local machine? Yes, sure. So let me share my screen again. So if you go to Muse and here if you click API, you can see there is an example which you can use in your terminal or any Python file, Python module, to send the request, send the prompt, and generate the image. So the I have imported request, and in the request I have specified my prompt and the quality of image. So I want high quality, I can set true. For faster version I can set false. And the response.json would contain the base64 image. So here is a sample response image which contains base64 encoded image. So you can just copy it and run it in your terminal or your Jupyter notebook, anything. So just go to Lightning Muse app, click on this API tab here, and you will get this.
So, we have one more question from LinkedIn. Do you have a planned session for creating apps to train models?
Do you have a plan session for? Yeah. So I'm not 100% sure about that, but we do have some apps which you can use to uh, train models. So you can go to the Lightning App Gallery. We have you can explore those apps, and I will get back to you. You can ping me on the Slack community Slack channel, and I will get back to you with details about if we have a session planned for this.
Yep, I also want to add over here, I've put in the chat the link for our feedback form. So you can actually let us know in our feedback form what specific apps you're interested in, and we could plan sessions accordingly.
So if we do not have any more question, I can move forward with one of our community showcase. I want to showcase a project from Irina. So we participated in Hacktoberfest, and one of our community contributor has created this cool app, and it is a Lightning app of UI where you can. It is similar to the Muse app. You can enter a text prompt and generate an art from it. So the model used behind this is not Stable Diffusion. It is something called Disco Art. I think it is from Gina AI. And kudos to Irina for this building this awesome application. Also, if you want to contribute and build some Lightning app or component, you can go to our awesome Lightning repository. So this is our awesome Lightning repository here. So if you go to the issues, we have a bunch of different ideas for apps and components, and some of it are already being contributed from the community. So you can pick one of it, or like if you have a different idea, you can comment here and we will assign it to you. Also, I would like to like focus here that this is built for Lightning community, and it doesn't directly come from the Lightning core contributors or the Lightning AI organization. So uh, we accept all the community contributions, and you might see that the code quality of this repo might not be as high quality as the Lightning core repository, because we have given a good war for everyone to contribute to this. And so if you build any application or component with Lightning, please do it with this hashtag build with Lightning and we will feature you in one of our coming live stream. And here are a few of the resources. So first, lightning.ai/muse, which has the UI for trying out Muse. You can play with it, and which also contains the blog link, and you can learn more about the code and everything in the blog. Then discover what Lightning can do in 5 minutes. So this is a quick start. It tells you the different features of Lightning in 5 minutes. And join our meetup group, PyTorch Lightning. This is the link to know more about like our upcoming events, and also join our Slack community to ask your questions, and if you have any idea about anything, you can ask it right there in the question channel. So thank you everyone, and hope this was a good live stream where you learned how you can scale your diffusion models or any kind of machine learning models with Lightning AI. And if you have any feedback, please scan this QR code, enter the your feedback. We will definitely take care of it in our coming sessions. So thank you.